service oh, sorry, there is a mistake. Okay, and he's from the the paper is co-authored by two other authors from Enrique Aguilar and Pines Albert.
So, hi everyone. Thank you for the introduction. My name is Isaac and I'm from the Israeli Meteorological Service. And as you can see from the title of my talk, times and temperatures are changing. We all know that we are all witnessing to the rise in the global temperature over the last 3 decades, and which is expected actually to increase based on the projection of climate models simulation. Well, in my talk, I would like to highlight a methodological issue, which I believe we should bear in mind regarding the problematic impact of different base period selections, especially under warming, accelerated warming trends and or under non-stationary conditions. This work was done during my PhD studies, supervised by Professor Pinchas Alpert and Dr. Enrique Aguilar. Apparently, the influence of selection of different base periods may sound to some of you or to all of you quite trivial, but it turns out that this is not the case for some indices which are widely used by the community for monitoring climate change. So before we will get into details, I would like to start with an example to demonstrate the main point and the motivation. So here you can see a map that depicts the trends for the tropical nights, when the tropical nights index is a day count index that counts the number of nights when the minimum temperature was above 20 degrees. So all the trends here are over for the period 1988 to 2017, when the reference period is 1961-1990. And now I would like to raise a question: how this map will look if we will change the reference period to be 1988 to 2017. Again, we are looking over the same period of interest. And if you didn't find any changes in these maps, you are right, because the maps are identical. To give you more intuition, let's see the slopes, the time series of this tropical index night index. Here is the time series when anomalies were relative to the period 1961-1990. You can see that there is an increasing of 6.7 days per decade in that index. And this is how the time series look when our reference period is 1998 to 2017. We can see that the slopes remain the same, whereas the intercept is the only thing that was changed. So basically you can choose any reference period, the slope will remain the same. The problem is that this association doesn't hold when we are looking on indices that their threshold were defined by percentiles. So please see the following example. Now for the warm spell duration index, again, the same methodology, the trends are for 1988 to 2017, and the reference period is 1961-1990. This warm spell duration index is a percentile-based index which counts the days with at least 6 consecutive days when the maximum temperature was above the 90th percentiles. Now let's see how this map, how this trend for the same period of interest look when percentiles were derived from the 1998-2017 base period. It is very clear that these two maps are totally different, although they are presenting the trends over the same period of interest. Black circles denote no trends. So now let's try to figure out why is that. To those of you who are not familiar with the percentile-based indices, I will give a very quick overview on percentile-based indices. I won't get into much detail on the way they are calculated and more aspects that are relevant for these unique indices. Then I will show some more examples regarding the warm and cold spell duration and the frequency of warm and cold days and night indices. And we will end with some take-home messages. In our study, we decided, in our study, did the slide change?
No.
No. Okay. In our study, we decided to focus on the most widely used percentile-based indices, which you can find in many papers and in the IPCC report. These indices were recommended by the expert team on climate change detection and indices and the expert team on specific climate indices. These indices actually looking for when the temperature was above a specific percentiles, for instance, when the temperature was above the 90th percentiles, or when temperature was below the 10th percentiles, such as the number of cool days, cool nights, and warm nights, and other indices such as the warm spell duration that we have just saw in the previous example. There are indices for cold spell duration that looking for at least 3 consecutive days when the minimum temperature was below the 10th percentiles. The rationale behind these indices is that they actually allows you to compare between countries, between regions, because we are using percentiles and not a specific threshold, the fixed threshold. Of course, this comparison can be done only if we are maintaining the same analysis and using the same formulas. Now let's see how this threshold look like. Here is an example for the maximum temperature when the 10th percentiles here in the lower curve and the 90th percentile here in the upper curve were derived from the standard normal reference period 1961-1990. The Julian day is on the horizontal axis, so here is January, February, up here it's June, July, August, and we're ending with November, December. Now let's see the percentiles when they are derived from a much warmer base period, from the last 30 years. It is well evident that the threshold are much higher when we are comparing these two base period. By the way, the same structure is for the minimum temperature. And what is and one more thing that we can learn from this graph are that there is a differential change between the two periods, meaning that there are larger deviation during the warm months and smaller deviation during the cold months. So there is no constant value that distinguish between these two periods. There is a differential change. To give you more intuition about this, please check the following maximum and minimum temperature anomalies for our region. First, it is well noticed that the trends are non-monotonous. We start with the relatively high temperature during the 50s, 60s of the previous century. Then there was a decreasing in the trend, in the temperature. And by the end of the 80s, the beginning of the 90s, we start with a continuous, steady increasing. In general, the long-term trends from 1950 until 2020 are 0.25 degrees per decade for the minimum temperature and 0.21 degrees, 21 degrees for the maximum temperature. And now let's focus on the last 30 years. We will see that the trends are much more stronger with a rate of approximately 0.6 degrees per decade. So now when we're deriving percentiles from this warmer, it's of course that their threshold are much higher if percentiles were derived from a relatively colder period, such as 1961, 1990. Of course, it should be mentioned that this period is relatively cold only relative to the last 3 decades and not relative to the beginning of the previous century, for instance. Let's go back to this example that I start with. And as I said, these two maps display the trends over the same period of interest, 1988-2017, and they are dramatically different, and they are telling different stories. Let's see their time series. I will explain this graph. The blue lines denote the time series when percentiles were derived from a colder, relatively colder period, 1961-1990, whereas, and the red lines denote the time series that percentiles were derived from the last 3 decades. We can see that for the last 30 years, there is an increasing trend of 8 days per decade in these indices when percentiles were derived from 1961 to 1990, and only 1.5 days, an increasing of 1.5 days when percentiles were derived from a much warmer period. So what is actually happening here? I'll try to explain it in another word. If we look on the red line, when percentiles were derived from the warmer period, as I said before, the thresholds are much higher. The absolute value of the temperature is much higher relative when we are deriving the percentiles from the cold period, relatively cold period. So if now we need to exceed this higher temperature, the rate of the exceedance is relatively quite low for the past, and it is quite low for these days as well. This is not the case when percentiles, when the 90th percentiles in this case, was derived from a much cooler reference period when the thresholds are lower. So the rate of the exceedance is much faster during the last 3 decades. And believe me, as one that lives in the East Mediterranean region, we're feeling this tendency, these trends of the warm spell duration, the frequency, the increasing in the frequency of warm spell, the increasing in the warm night and warm days. We really can feel it as a resident of this region. The opposite goes when we are looking on the cold spell duration. We need to, here the threshold is the 10th percentiles. We need to be below this 10th percentiles. And when looking on the last 3 decades, we can see that when percentiles derived from a warm period, such as 1998-2017, we are getting a decreasing of approximately -7 days per decade, which is 3 times, even more than 3 times higher if percentiles were derived from 1961-1990 with a rate of a decreasing trend of -2 days per decades. Now an example for another widely used, widely common indices, such as the cold days, the warm days, cold nights, and warm nights. Again, all these panels display the trends over 1998-2017, when the reference period is the cooler one. We can learn from it that there is a decreasing trend in the number of cold days and cold nights. And on the other end, a well-pronounced, a stronger increasing in the warm days and warm nights. Now, if percentiles were derived from the recent period, we are getting a totally different picture. Now there is a strong decreasing in the frequency of cold days and cold nights, and only a mild, moderate increasing trends for the warm days and warm nights. And again, all these maps depicts the trends over the same period of interest, and they are telling different stories. These are their time series. And as I said before, when looking on cold indices, such as cold days and cold nights or cold spell duration, there is, when percentiles were derived from the warm period, we are getting an increasing trend, much stronger trends relative to the time series when percentiles were derived from the cooler period. The opposite goes for the warm indices, such as warm days, warm night, warm spell duration, when percentiles were derived from the recent three decades, the trend magnitude is relatively lower than if they were derived from the relatively cooler reference period. More information can be found in our published paper. So if now I will conclude the presentation. So we saw that percentile-based indices are much more sensitive to the selected base period compared to alternative indices. As we saw, the indices with a fixed threshold, a day count indices, the number of days that were above 35 degrees, or the number of days that were below 2 degrees. It doesn't really matter which reference period you will choose, the trend magnitude will be the same. We saw that there is a differential change in the annual cycle. There are larger deviation during the warm months and smaller deviation during the cold months. So there is no constant value that distinguish between these two periods. The magnitude of the warm indices is dramatically diminished, as we can see here, while the trend magnitude of cold percentile indices is strongly amplified when percentiles were derived from base period that included records from the last 2 decades. So, and this phenomena is even more pronounced when the study period covers only the last 30, 40 years. Using a recent warmer base period may lead to erroneous conclusion that there is only a slight increasing trend in the warming indices and the opposite for the cold indices, where they are characterized by a strong decreasing in the number of cold nights and cold spells duration. Last remark, to properly compare or integrate data from studies that uses percentile-based indices, the base period should be the same, especially in this area characterized by accelerated warming, and it is expected to increase based on these different scenarios. So if your study involves percentile-based indices, I think that we should bear in mind this overestimation or underestimation trend magnitude that you may have. By the way, the WMO, even one of Jose's slides showed it. The WMO defined the period from 1961 to 1990 to be the standard reference period for long-term climate change assessment. So if we wish to speak on climate change, it is better to stick to this standard normal reference period, especially when we are using percentile-based indices. So thank you very much for your listening.
Thank you also very much. And I think we have just time for 1 or 2 short questions. And I give the word to the audience.
Those of you who would like to ask a question, use the raise hand button on the bottom of your screen. Hollis that wants to ask a question.
Okay, thank you, Thanos. Thank you very much for the presentation. That was really interesting. If I understand rightly, the cause of the results that you're seeing is because of the differential change is different in the summer months and the winter months between the two base periods. So I'm wondering whether if you did a separate analysis, say for the 2.5 years, do an analysis for the summer months and a separate analysis for the winter months, whether you would see a smaller effect or a more robust answer in terms of the trend.
Thank you for your question. Yes, you are right. And in our paper, you can see the differences regarding the different seasons, and the highest significantly difference was occurred during the summer, and in some indices for the autumn and the spring, and the changes for the winters were not significant. Yes, this is a good remark.
Okay, thank you.
Thank you very much. I think we should proceed now to the next presentation given by Guerrero y Llanza from the Spanish Meteorological Services or University. And I give the word to Jose again.
Thank you. Let me share the screen. Are you seeing the presentation?
Not now.
No? I must click on the share button. Maybe now?
Now it's okay.
Okay, thank you. Okay, this is the title of the presentation: Uncertainties of Observed Surface Temperature Trends, the case of the Balearic Islands. Summary would be, well, after an introduction, I will show you two contradictory messages, and then followed by the published trends on Balearic Island temperature trends. We will show then an update of these temperature trends in our archipelago. Also, the trends calculated from reanalysis and from gridded products, and followed by the conclusions. Well, there were two contradictory news in local newspapers in the first year of this year, stating that observed surface temperature trends in the Balearic Islands were the highest and the lowest of the whole Spanish territory. Both affirmations were allegedly derived from published reports issued by authoritative sources, raising the interest to investigate the reasons for such opposed conclusions. Moreover, this exemplifies the difficulties to communicate certain aspects of climate change to the public, since contradictory messages undermine the credibility of the climate science. These are the two examples, the two contradictory messages that were published. To the right, it was in a newspaper, to the left in digital media. To the left says that Balearics is leading the climate warming in Spain, while in the right says that Balearics Islands is one of the regions where the temperature has increased less from 1961. This is a table, summary of published trends in degrees per decade. Here you see the several references, the periods, which you see are quite different. Number of series also, most of them were limited to the more complete series. There were 4, 3, even 1. In 2 of these published reports, 48 stations were used, but many of them were very short. Also, to the right, you see that all reports were about the mean temperature, but some of them separated the trends from maximum and minimum temperatures. And also in bold, you see which of them have used homogenized series, while the others were using raw series. You can see in this table that trends are so varied as, for example, for the mean temperatures, so from 0.11 degrees per decade up to 0.77, which is really a big difference. Well, let's see an update of the temperature trends from the Balearics. The period will be this 60-year period from 1961 to 2020. 80 series of monthly averages of maximum and minimum temperatures, which have a minimum of 10 years with data in the period. The development version of the Climatol R package was used for the quality control, missing data estimation, and homogenization of the series. Trends were calculated for different numbers of series depending on the threshold imposed on the percentage of available data. Trends were compared also with series derived from reanalysis. And finally, trends were calculated for area averages of gridded homogenized data. This is a display of the availability of data for the maximum temperature. Is the same for the minimum. And you see that most of the series are very, very short. In this next slide, you can see the geographical distribution classified by colors depending on the percentage of available data. Here you have numbers about these percentages on numbers of stations. There is only one which has more than 90% of stations. If I can remember well, it was the Ibiza airport. 80% of data, more than 80%, are available in 4 stations, which are the 3 airports, the airports of the 3 islands, and also mountain station over here. Look. And I will show also calculated trends for the 22 stations which have more than 50% of data. This is an example of a very neat inhomogeneity. This is a very exaggerated inhomogeneity located in this station, Manacor. Here you can see the correction. The inhomogeneity was a jump in the mean of nearly 4 degrees, which is very, very high. If I remember well, the reason was that the previous location was very badly sited in a shady yard, so it had a cold microclimate. Here you see the reconstructions of the series from both homogeneous subperiods. In black, you have the original data, and in red and in green, the reconstructions of the series. Normally, most homogeneity methods provide you just the reconstruction from the last homogeneous period. That would be the red graph in the upper side. This is another significant inhomogeneity. Has a SNHT of 91, although it's not so neat as the previous one. But this is an example of most common situations. Well, let's see the graphs of annual average temperature of raw series in dashed lines, and the homogenized series in red, in continuous line. Here I have shown the Luke series in blue, which is that station in the mountains, hence the lower temperatures. Palma and Ibiza airport in the upper side. The Minorca series would be over here. It has been excluded to avoid a too messy graphic. We can see this is very common in Europe and in other parts maybe of the world, of the diminishing temperature by the beginning of this period and then rising again in the rest. Here we can see the trends for the whole period, 1961 to 2020. for the two variables, the maximum and the minimum, and also for the raw and homogenized series. Every three box plots, we have the calculation is made from the 4 more complete stations, the first box plot. The second one is for the 8 stations, and finally for the 22 stations that had more than 50% of data. You see that depending on the number of stations that you get, the trends can be very different. And also you see here in orange maximum trends for maximum temperatures calculated from raw series, and in red you have the same but calculated after homogenization of the series. You see that the values are much more consistent between them than before the homogenization. That's something that we already know. The same to the right for the minimum temperatures. In green, we have the for 4 stations, 8 stations, or 22 stations, the rise in temperatures calculated, the trends for the raw, from the raw series. And in cyan, we have the after homogenization. Depending also, although the trends are more similar, there are still substantial differences in the median, for example, depending on the station that you use to calculate the trends. These are the maximum trends, the monthly, in monthly trends for all 82 stations after homogenization. And you see that most of the months have a very strong trend, warming trend. Only the coldest months have a more moderate increase in the temperatures. With minimum temperatures, we see something similar. Most of the months have rising temperatures, quite significant. Even in December, we have a very strong trend, warming trend. And we have a curious anomaly in the September month, which is one of the more moderate in rising. This is something to be investigated. Why is so different September from the other months? Well, for the calculating the trends from reanalysis, the reanalysis were drawn for the closest grid points, one from NSAP, NSEP, and CARD, and 3 from the 20th century reanalysis that were downloaded from this address. I will show you what's the map again to show you the location, which I didn't comment it before. The NSEP is 1 point here, which is the grid point, the closest grid point to the area. And for the 20th century reanalysis, there are three grid points here in pink. As the 20th century reanalysis series stopped in 2015, the version 3, the last 5 years were infilled using the NSEP and CAR series as reference. Trends and mean annual temperature for these 4 points are compared with the trends of the 4 homogenized, more complete observational series in the next slide. Here you have the homogenized for Duke and Palma, Maui, Ibiza, and the reanalysis. Reanalysis are very similar between them. And there is this, for the minor islands, the trends are slightly lower, but anyway, the confidence intervals are overlapping. For grid trends were calculated from the homogenized series, and the time series of these averages of the 3 grids are very similar. The running trends for different temporal lengths show how different the results can be depending on the period used to calculate the trends. You can see here that first the cold trends for short windows at the beginning of the period, then the highest increase in warming temperatures. But as we increase the size of the window, the differences are less important. This is the time series of the island average temperatures from the gridded products. We see here this strong decrease in temperatures, followed by also a strong increase. So the 30-year periods here would have almost non-significant increase in the trend. Then this will show a highest increase in trends. And also over here, there is a warming, but not so big as before. So depending on the period, we can have quite different trends, evaluation of the trends. Here we show an example of what would be a 30-year running trends for the 4 stations, Palma, Minorca, and Ibiza airports. And you see here that the null trends at the beginning of the 30-year, the highest trends over here, which are nearly 0.7 for Luke. And then the trend is not so high. And the last 30 years, we have around 0.2 per decade, 1/10 of degree more for the Palma airport, and 1/10 of degree less for the Ibiza airport. So for the conclusions, we have that climate series must be homogenized to avoid misleading results when studying the variability. Different ways of calculation may produce substantial differences in the temperature trends. The greater differences are influenced by the time period chosen to calculate the trend. Should we promote the use of a standard period, for example, the previous 30 years? And special care must be taken in communicating these varied trends to the public to avoid loss of credibility of the climate science. That's all. Thank you very much for your attention.
Thank you very much, Jose. You just said what I wanted to say, that it's really very, very important to say clear what we are calculating, and also that we say this message to the people who are publishing, what is the standard period taken and so on. But I won't give the floor to the speaker, to the questions. Are there any questions?
I'd like to remind you that you can use the raise.
Can't hear you.
Okay.
I suppose there are no questions?
I don't see any raised hands, Inge.
So if there are no questions, and I look at the program, is it true that we have now a break for about half an hour?
Yeah, it was scheduled like that. So we will reconvene at 13:10 Athens time.
Okay, thank you.
Very much.
Okay.
Geiger of the Köppen climate zones in Spain. But I have to say, Andres, please be as short as you can, because we have lost some minutes with this late presentation and we want to stay on the timetable. Okay?
Grace, can you hear us?
Hello, can you hear me?
Yes.
Yeah, no, it's okay.
You can start. You can use the share screen button on the bottom of your screen. Share your presentation. Can you hear me? Cannot hear us.
Okay. Okay, can you hear me, please?
Yes.
I can hear you.
Can you hear us?
Okay. Okay, good afternoon. Well, I am Andrés Chatara from the Spanish Meteorological Agency. I'm sorry I'm very late, so I will make a short presentation. And in this presentation, we are going to analyze the temporal evolution of the Köppen-Geiger climate zones in Spain from 1951 to 2020. Well, as you know, this is a very old climate classification. It is more than 100 years old, but it is still nowadays one of the most frequently used climate classifications. It is used in climatological studies, and it has been also frequently used for climate change impact assessment. So in this study, we have used greedy data sets of monthly temperature and precipitation that have been recently published by the Spanish Meteorological Agency. These are two technical notes with these publications. And regarding the generation of the grids, we used multiple linear regression with ordinary kriging for the temperature with some independent variables, and ordinary kriging for precipitation. And we considered two study areas, the mainland Spain and Balearic Islands, and on the other hand, the Canary Islands. These grids have a spatial resolution of 1 per 1 kilometer. We generated climate classification maps for consecutive 30-year reference period and maps using 30-year moving averages for analyzing the climate zones in the study period. And now we are going to see the results. And first, the Köppen-Geiger climatic classification in 30-year reference periods. On the left, we can see the climate classification for the first period corresponding to 1951 to 1980. And as we can see, in Spain, we have many different climate zones. We don't have tropical climates type A, but we have the other 4 main climates. And as you can see, there are arid climates in the southeast of Spain, some also in the plain in the center of the country, in the northeast. And of course, in the Canary Islands, we have even desert climates types, type BDD in some islands. The temperate climates, type C, are the most common climates in Spain, and they are represented in green and blue colors. And the continental climates, type D, are represented in purple colors, and they are only in the mountains, in the Pyrenees, Cantabrian Mountains, and other mountainous regions of Spain. And finally, we have even polar climate, type E. It is very difficult to see it, but in some places in the Pyrenees, in the highest peaks, above 3,000 meters of altitude, there are some small points here in black color, in white color. And well, on the right, we can see the following climate classification map, the following 30-year reference period, and we can see how the arid climates have expanded compared to the previous period. And in the 2 following periods, that expansion of the arid climates is even more evident. We can see how the areas that were separated in the southeast and in the center have expanded, and now they are connected. And well, in the Canary Islands and in the Balearic Islands, the changes are more subtle. And it is interesting to see that here in the 1981 to 2010 period, the polar climate that was remaining in the Pyrenees totally disappeared. So it became extinguished since this 30-year period. And this is the last 30-year reference period. And we can see how the arid climates have expanded over large regions of Spain. Well, here, this is a map with the changes that we have observed since the first 30-year reference period and the last one, considering only the main climates type, the main types of climates, only the first letter of the Köppen classification. And in gray colors are represented the areas where there have been a change. So we can see here the expansion of the arid climates and how the continental climates have shrunk in the mountainous regions. And as I have said, in the Canary Islands, there are only small changes, as well as in the Balearic Islands. And well, just in order to analyze with more detail these changes, we also applied a 30-year moving average to the temperature and the precipitation grids and calculated the resulting climate classification maps. And we have represented the graphics with the temporal evolution of the percentage of the area occupied by each main climate type. So here, in the study period, in the study zone of the mainland Spain and the Balearic Islands, we can see how on the left, the type P climates, the arid climates, were almost constant during the first decade. And after 1990, here in the horizontal axis, we have represented only the last year of every 30-year moving window. So after 1990, it began to grow quickly until 2010 approximately, and then it became again constant. So it changed for approximately 10% of the area to 20% of the area. Meanwhile, the evolution of the sea type is almost the opposite. It remained almost constant during the 80s, and then it quickly decreased in the 19th and the first decade of the new century, with an area loss of about 10% of the territory. The continental type, and type D, it reduced their extension, but in this case at a steady rate, going from 2% of the territory to less than 1%. And finally, the polar climate E shows a very rapid area loss rate during the first decade, and it completely disappeared in the mid-90s, just for the scale that we have considered in this study, that is 1 per 1 kilometer cells. Well, these results are in accordance with the observed melting of the remaining glaciers in the Pyrenees. As we can see on the right graph, they have been reducing their area in the 2 last centuries, but there has been an acceleration of the loss rates in the last decades, as we can see here on the right of the graph. And recent studies suggest that the last glaciers of the Pyrenees will probably disappear in 20 or 30 years from now. Well, in the Canary Islands, the changes are more subtle. As we can see here on the left, the arid climates have increased its area, but with some oscillations. And the climate C has decreased from 36% to 51 approximately, but only with again with some oscillations. And the climate D, that is located only in the highest mountains of the Tenerife island, in the Mount Teide, has decreased its area, but only during the last decade. So to end up, well, we have prepared a short video. I'm going to play it, where we can see the 30-year moving average maps. So I'm going to play it, and yes, we can see how the arid climates are expanding with some temporal contractions, but on the whole, they have clearly increased their area. Well, I have here to sum up some conclusions, but I have this is only a sum up. So, well, I think we can stop here. So thank you very much. Sorry for my delay. Thank you.
Thank you very much, Andres. And I propose that we have discussion on your presentation maybe afterwards in the discussion round, and would announce now the next speaker, which comes from Hungary. Monica Lakatos and Oliver Sentes will talk about the analysis of sub-daily precipitation extremes in Hungary.
Thank you very much, Ingeborg. I try to share my screen. Can you see my screen?
Yes, I can see it.
So I switch to the okay. So good afternoon again, everybody. My co-author is Oliver Sentes. He also will give a presentation late afternoon. So what was our motivation? The precipitation have been becoming more intense in Hungary, as in many parts of Europe and the globe. You can see here the days with more than 20 millimeters per day from 1901 to 2020 on homogenized and gridded daily precipitation data. The countrywide averages can be seen each year, and you can see that the largest values appear from the late 90s. The other thing, what was inspired, what inspired us was that we prepared recently a climate service for engineers for the urban planning and drainage systems, and we are going to improve this service. And in the second part of my presentation, I will give an outlook for the subdaily precipitation extremes to the Pannonian Basin in the frame of an international effort, the so-called Pannonian Basin Experiment. So here you can see on the right-hand side a snapshot from our user service. The engineers can enter the geographical coordinates where they are planning a drainage system or an object. And when they enter the geographical coordinates, the closest station appear in red, and the other 4 close stations are depicted in green, and also the table with different return levels for 10 minute, 20 minutes, 30 minute, and 80 minute rainfall depths values can be downloaded from this publicly available service together with the guidance here. So we developed this service together with the members of the Chamber of Engineers. So this service is based on automatic measurements from 1998, and we regularly update this, and we applied the GEV distribution fit to get the return levels for different return periods. But we agreed on that longer data series are needed. So if we fit the GEV distribution for a short period, the confidence intervals will be very wide. So we are going to reduce that by including longer data series in this user service. But unfortunately, the sampling changed from the mid-90s due to the installation of automatic weather stations. Before mid-90s, ombrometers data were recorded. So from the ombrometers registering paper, the maximum of the different short term, so 5 minute to 3 hours minute rainfall depth per event were recorded. So this type of recording gives rather intensity than a partial sum, but recently the automatic measurements recording. So we have around 100 stations, 10 minutes partial sums, which are entered the database real time, and we also have 1 minute sampling, but available only for a few stations, around 10 stations in Hungary. So here you can see the yearly max from 1967 for a selected station from the southwest border in Hungary. We simply merged the data recorded from ombrometers registering paper and automatic weather stations. The largest values can be found in the last recent years. We decided to downscale the 10-minute data to make possible to choose the most intense partial sum, as they could have been recorded from the ombrometers registering paper. So we have 10 minutes data, and we downscale that to 1 minute. We used doing that for 10 minutes interval, 2 before and 2 after a specific 1 minute to this multiple linear regression process. So we estimated the 1 minute data from the 10 minutes data, as you can see here the formula. And we can do that for all stations where 1 minute's data are available. Here you can see the differences of the yearly max from 1 minute downscaled and the 10-minute observed data for the automatization periods. So there are a little differences between the most intense partial sum based on the 10 minutes data and from the downscaled 1 minute data. The largest difference for 10-minute partial sum is 1.2 millimeters, and for 20 minutes 1.8, for example. So we can do that downscaling process for the rest of the stations where 1 minute rainfall depths available. We are going to look into this to check if the coefficients of the multiple linear regression has some regionality. And after this downscaling process, we can extend this user service back to 1967, about 20 stations. So let's move to the second part, to the international collaboration, what we have done in the WMO GVAX related initiative, that the so-called Pannonian Basin Experiment. We prepared a special issue, and we, together with the 8 meteorological services in the region, we contributed with an article with the title that Analysis of Subdaily Precipitation for the Panmax region. We analyzed early precipitation data. The data series had different lengths from 1950 to 2019. There is another GVAX related activity, the so-called INTENSE, which is a crosscut under the umbrella of GVAX. And in this project, the Newcastle University, a team in the Newcastle University prepared a computer program for quality control and for deriving some climate indices for subdaily precipitation. And in this activity, we used this computer program commonly. The calculations are carried out on data aggregated 1, 3, and 6 hours intervals, and we choose some selected indices. Here you can see the area in focus, and on the right hand side there is a graph where you can see that you can see the by country data availability for this study, the number of stations included, and also the percentage of the missing data are different for different MET services. For example, there are some stations go back 1950 or even earlier, but there are a lot of missing data in these data series. Most of the data from Austria, Czech Republic, Slovakia, and Hungary goes back late 90s, and these around 20 years period were used mainly in this analysis. I've mentioned that we had a collaboration with the Newcastle University. They are working now on put together a global data set of observed subdaily precipitation or at least indices. And with this collaboration, we contributed to this global data set as well. We used the common computer program I've mentioned, and the input was either the early or the 10 minutes data. You can see here the selected indices, the simple maxima of 1 hour, 3 or 6 hour precipitation, count of 3 hour periods greater than 20 millimeters, and maximum length of wet spell, timing of wet test hour, and mean precipitation. So these list of indices were analyzed in the article what I've mentioned. The main aim was to assess the general climatology of the region. So on the left column, you can see the annual average, and the right column, the maximum of a 1, 3, and 3 hour rainfall depths, and the range of the values are related to the size of the circle, and the colors are distinguished the different time period what were available for this study. Here you can see the seasonal averages of the 1 hour precipitation intensity in the region with the same coloring of the different time periods. And here you can see a result of a trend estimation. So the decadal change of the mean 1 hour precipitation intensity can be seen from 1998. The largest increase can be seen in summer. Almost 70% of the stations show an increasing, but less than 15% is statistically significant. The statistically significant increase are circled. And also autumn can be seen some increase, but less than 15% is significant here. Here are some indices for selected stations. Szeged is located near the south border in Hungary, and Belgrade is the capital of Serbia. So we have chosen 2 stations from the Pannonian Basin here. To the left axis, the columns represent the count of 3 hour periods with greater than 20 millimeters, and the right axis show the maximum. The graphs show to the right axis the maximum length of wet spells. And for the same stations, you can see the timing of the wettest hours. So you can see the hours here from 0 to 0, and also the months here, and the months here, and some concluding remarks and the future plans for the rest. So we have a downscaling method prepared from 10 minutes data to 1 minute rainfall depths, which is available for further study. And we developed the service for urban planning, and it can be updated with the longer data series, goes back mid-90s for 20 stations for Hungary. So we are going to examine the regionality of the fitted GEV distribution for these stations, and we are going to make additional data rescue to get all the registered data on the ombrometers registering people paper to digitalize and to enter the database. And we are thinking on rescuing the data as it could have been measured by automatic measurements. And we are planning further collaboration in the PANNEX to include more stations and maybe Ukraine to this activity, and also to include more indices in the analysis. Thank you for your kind attention.
Thank you very much, Monica. I ask the audience, we have time for 1 or 2 questions. Please raise your hands. There are some.
I think it's Joseph, yes.
Yes. So we start with you, no? You have a question?
I have a brief question, if I may, sorry. Monica, is this Python routine available through a repository or something?
I suppose so. So it's we contacted the author actually, but they are glad to share the knowledge. Yeah, I think if you would like to, I can share his email address.
Great.
And there are several articles on this intense project where this computer program was developed. But recently, that computer program was updated, so it's worth to contact directly the authors for the most recent, to get the most recent version.
Great, thank you very much.
Okay, Joseph, please.
Hi, Monica. It's good
Hi.
to see you, and thank you very
Nice
much
to see
for.
you.
Thanks, and thank you for your kind presentation. I saw that in one of your slides that you took the historical ombrometers records and combined them with the automatic weather stations data. So I'm wondering if you made any did you homogenize the time series, or maybe you have some parallel measurements in order to understand the difference in these two measurements?
We are in the very beginning of this work. So the graph you mentioned, we just simply merged the data.
Mm-hmm.
So
Okay.
the first part of the graph was from the ombrometers era, and the second part from the automatic measurements. So the main problem is the main inhomogeneity, or maybe I cannot say that's the problem of inhomogeneity, but the sampling was different. So recently we are going to prepare a data series as it could have been measured continuously. So the problem is that it's not simply a homogeneity problem. It's so the most intense period in a per event is a different climate element than the 10-minute sum or the 20-minute sum. So it's not the homogeneity problem, in my opinion. It's the sampling.
But do you have any problem. But do you have any parallel measurements to verify this issue?
The problem is that the yearly max, for example, is from summertime, and we had several months or maximum 2 years parallel measurements, and it's not enough to explore the similarity or to make a simple dependence between these two types of elements. That's why we decided to downscale the data.
Thank you very much, Monica.
Okay, and Chatara, you had a question?
Very brief one. Thank you, Monica, for your presentation. Very interesting. I was wondering, on one of your slides, you're showing trends in this extreme precipitation and in summer, and in most of the stations you see a positive trend indicating that the extreme precipitation is on the increase. But there were also a few stations showing a statistically significant decrease. I was wondering, did you have a chance to look at it in more detail, and could you provide some ideas on why that is? Because that's not what you'd expect, right?
Yes, it sometimes is confusing that in not too large distances there are increase and decrease, but the increase was not significant and the decrease was significant. Yeah, it's we have to analyze these details later, but yeah, I experienced this on not only out of the borders but in Hungary, and it's not so easy to communicate that. Yeah, you are right. You are right.
Yeah, it's difficult. Thanks very much for your answer.
Thank you, Monica, for your presentation. And
Thank
we
you.
move on to the next one, which comes from Germany. It's climate monitoring in Germany. Overview of recent improvements. Oh, yes. And I invite Frank Kasper to speak.
Yes, okay. So I have to select the presentation. Well, now I'm confused here. I just take the full screen.
Great.
Can you see it?
Yes.
Okay. Yeah, so as announced, I'm going to talk about our recent activities. And when I look back at the activities of the last 12 months, for example, this is not so much about the methodology itself, but it's more about communication. We already have heard that there is a new reference period that ended with 2020. And so I will mainly focus on well, tools and communication, but I will also give some details about our data and frequently asked questions that are addressed by the public towards our results. So what you see here is a typical result of our activities. So the temperature analysis for Germany starts at 1881. So we typically say that's a date where systematic weather observations have started in Germany. And what you see here are the annual anomalies as compared to the reference period 1961-1990. And what you clearly see, as probably for all the countries in Europe, we have a temperature increase. The linear trend is plus 1.6 degree, but we also see that most of the recent years are much above this linear trend. So this linear trend also is more and more inappropriate to really describe the behavior of the temperature trend in Germany. And we also had the discussion on the reference intervals. So here you see with different colors the mean values that we get when we calculate the 30-year interval starting at 1961 or 1971 or 1981, or the most recent 30-year period that started 1991. So you see that there is always an increase, and we had discussions with our press department, so what we are going to use for the communication of the monthly anomalies in Germany in the future. So, but at the end, the discussion led to the same conclusion as also is given as advice by the WMO. So we stick to the 1961 to 1990 value as a reference when we talk about climate change in Germany. And well, I have some examples on the consequences of that. So it started already with January of this year. So when you look at the anomalies of January, when you compare it to the old 1961 reference period, it was 1.1 degree too warm. But when you look at the most recent 30-year period, the January was actually too cold. And so some of the climate skeptics criticized that approach. Their argument was we are doing that by purpose just to well, just to communicate it is too warm in every month. But I mean, that is the reason for doing it. So we just want to compare if the well, what the climate state is currently as compared to the long-term average. But for example, in some user-specific applications, for example, in the agricultural department or so they look at more recent intervals if that is relevant for their customers. So here is an example how our results would look like if we would move to the most recent 30-year interval. And you clearly see that the most recent long-term average for 30 years is even above the linear trend. And you still see that everything what is red, what is warmer than this average is really focused on the last few years. And this led to the discussion if we should change the general approach and avoid the linear trend. But when we do this, we also want to be consistent with what our neighboring countries do, or also what international organizations do. So it was quite interesting to see that in the most recent IPCC report, in the summary for policymakers, the IPCC did not use a linear trend anymore, but they moved to the comparison of 10-year intervals. So when we do that for Germany, the most recent 10-year interval was 2 degrees warmer than the beginning of the analysis period here. So you see this obvious difference. So if we take the linear trend, it's 1.6, but with 10-year averages, as the IPCC does, it's 2 degrees. So there is some confusion in the public about these different statements. And currently, we just try to solve this by communicate as clearly as possible the methodology that is behind these results. I promised to talk a bit about communication. So as you see here, we use a Twitter channel to bring these results quickly into the public. So on the left, you see the typical tweet of our department that was from 4th of January. So it's just a few days after the end of the last year. So we have this result rather quickly in the public, and we see that the media is picking that up. So on the right, you see the same graph that has been used in one of the main news outlet, public ones, second German television channel here. And you see that this way of communicating the results works quite fine. But also we get a lot of critical questions. So when we start to use social media for the communication of these results, then also a number of people comment on that, that don't want to believe in our results. Let's put it that way. So the first questions come up related to the network. So mainly the people argue that, well, we don't compare the same network, we don't compare the same measurement technology and things like that. So we are typically prepared to explain all this. And for example, the network, we have the advantage that all the data are published under an open data license. So people can directly go to our data portals and have a look at the situation of the network at the beginning or at the end of the observation period. So here you see the examples for January 1881 as compared to January last year. Of course, there is an obvious change in the network. And in that context, we also have to explain that we do not just average the stations, but that we use a typical gridding approach, which produces a map for every year, as you see here. And also when you look at these maps, you see the increase towards higher temperatures. Of course, this gridding approach avoids the strong effects of the changes in the measurement network as compared to calculating a pure mean value out of the station data. So a lot of work has been invested this year into our so-called climate atlas. So this is a tool which allows you to directly have a look at the maps, also to have a look at the time series for a number of parameters. You can interactively select the parameters, the months or the region of Germany. And the interesting thing here is that it is combined with the results of climate scenarios. So you can get a monthly update of the observations and directly compare it, how it fits into the long-term picture here. And we get a lot of feedback on that. So people really like that idea that you have the possibility to compare the observations with the climate scenarios. And it took a while that we included the new IPCC's RCP scenarios. These scenarios itself are not yet really a new thing, but we had to run the regional climate models and also to run the impact models, because the system also includes several information from the specific sectors, as for example, the impacts in the agriculture or forestry or so on. So there was a release this year which contained a lot of improvements. So once again, this is just zoom into the map display here. So what you have on the left side is the gridded data from the observations, and on the right side you have different results from the climate scenarios. It's actually ensemble that consists of 21 regional climate models. So not only operated by DWD, but also available from other institutions. So again, this is a time series plot where you can see once again the merging of the long-term scenarios with the observations. Here it is important to note that we did not have the opportunity to use the 1961 period because the climate scenarios started just at 1971 in a lot of cases, and therefore to allow merging both informations, we had to move the base period to 1971 to 2000. Well, as I said, you can look at different regions of Germany. Here, this, for example, is Bavaria, and the parameter here is precipitation. And for the screenshot, I also moved to a different climate scenario. It's the RCP 8.5, and I selected a specific month, April. So what you see in the time series, it's that especially during the last decade, the amount of precipitation was significantly reduced in that month. So it's an especially strong signal for April. But well, it's relevant for the sectors because this is the start of the growing period in a lot of cases. And therefore, we had a lot of discussions on the droughts in Germany here. So we do not only use the internet tools for communicating the results, but there are also these conventional things like the press conference, which is given annually on the status. But we try to publish at the same date the so-called climate status report, which provides a summary of all these results. But it's written in Germany. So it's a public document. I have the links at the end of the presentation, but some of the tools you can switch it to English, but this report, for example, is only available in Germany, and also the videos that are provided on YouTube. So this is just one example, again, from the paper report. So this is a way of really communicating what do we see and how does it fit in the long-term scenarios, and what are the, for example, the opportunities, how will the result be different if climate protection will be successful. And I promised to provide a few additional information on the background and the data sets. So as all of you know, there is a lot of historic documents in the archive that are still not yet digitized. So this is just an example from 1828 in Frankfurt, for example, and we see that the public audience is really often interested in that because they do not really have a feeling what is the background of all this data, and this kind of visualization makes it really clear to them what the basis of our analysis is. So the digitization is a long-term effort, and here on the left you can see the different years of the activities. So it started more than a decade ago, so that some former observers were working on the digitization of the data, and the different colors just indicate how much stations they or which years of these stations they digitized within the specific year of activity. So you see that some long-term time series are added. These are the climate stations, which have a lot of or several meteorological parameters. And in addition to that, there is also the digitization of the pure precipitation stations. So they just measure precipitation. It's easier and quicker to digitize those. So the number of stations is higher here, and we are continuing with that. So we have an increase in the availability of the data each year. In addition to the availability of the data, so it's also important to understand the inhomogeneities, obviously, and argument that is easily understood by the public is the concept of the climate reference stations. So in Germany, these are stations where we operate the previous and the current measurement technology in parallel. So for temperature, that means the historic mercury thermometers are still in use, and they are compared with the automatic electronic thermometers. So the new thermometers, of course, they provide well, data with much higher temporal resolution, but this combination of both allows us to understand if there are systematic breaks. For the measurement conditions in Germany, we see that there is no inhomogeneity caused by the automation here. So there was not even a need for homogenizing that. So this histogram just shows the difference between the traditional and the recent way of measuring. And you see that the mean value is very close to zero. So as I said, there is no inconsistency due to this change in technology here. And this has been demonstrated at around 10 stations. And these parallel measurements have been operated for 10 years now in parallel. So it's a good database to really be sure that what we're talking about here. So the last thing is that already a while ago, we had a change to a very open data policy. So the first thing we did is just to provide the time series for pure download, but we invested also some time into creating an interactive data portal where you can browse through time, or you can click on each separate stations to also obtain the metadata. So it's not only the time series itself, but it has the information on the history at the stations, for example, the locations, the technology that has been in use, and so on. So, but it's, well, considering the wide range of data and different temporal resolutions and so on, it's an ongoing activity that will take some time until we have made all the data publicly available. Yeah, that's it. Yeah, here you have some links. It's just well, links to the things that I have mentioned. Either you can have a look at the time series or the climate atlas or the open data portal here. And now I'm available for questions.
Thank you very much, Frank. And I want to ask, are there any questions? We have time for one or two. Can't see.
Okay.
But in the meantime, can I ask you? You showed this comparison of manual thermometers and the modern ones. Have you done something with precipitation as well?
Yeah, we are currently also having a deeper look into that once again, because we are now changing the technology once again. Well, the conclusion for precipitation is somehow more complex than the result for temperature. Well, I think it's common knowledge that if you have to consider the wind speed or the ratio of snow and so on, and so it seems that the new generation of precipitation instrument in general has a quite good and comparable quality, but there are some specific cases where we need a deeper look into the details.
And do you have one question of Mary?
We
Sorry,
don't hear you.
Yeah, sorry, I was turning off my mute. Hi, Frank. Just about your reference climate stations where you have the parallel measurements. Are they available, the results from those studies, in a paper or on one of those links you gave?
Yeah, there is a very long report that is written in German and it's publicly available, but there are also some summarized conclusions in the in the scientific literature in English. I can point you to these documents. Perhaps you just send me an email or something so that I have your contact details, and I will be happy to provide this information.
Okay.
Or I can also add a slide here and with the references, and then you will find it in the material of the conference.
Okay, thank you very much. Thank you.
Okay, thank you, Frank. And Mary, you can stay, and now your presentation comes.
Okay.
About the production of the Met-Arens 1991 to 2020 solar climate normals for Ireland. Please.
Okay. Just see. I think, okay. Oh, it's saying that somebody is still sharing, so I can't share my screen. Okay.
Try now, Mary, please.
Okay. Yeah. Okay. You can see my screen now. Okay.
Yes, yes, you can see.
Okay, so my talk today is on the production of Met-Arens solar climate normals. The work was mainly done by Conal Ruth, but unfortunately he has an exam today, so I'm presenting the work for the talk. So there are a number of other people involved in it, but the main work has been done by Conal to date. Okay, so the parameters in this study are the total sunshine duration, the number of days with no sunshine, maximum daily sunshine duration, and then total global and diffuse radiation. This presentation mainly though focuses on sunshine duration. So for the stations, we have these 5 stations in green where we have global and diffuse radiation, and they also have sunshine recorders, so for sunshine duration. And then these orange stations just have sunshine duration, and these are shown in the orange here. We do have some other stations, but the records were too short to form normals from these stations. Okay, so the first step was quality control, and was extensive both manual and automatic checks carried out, physical limits taking into account the time and location, persistence, step changes, and comparison with duplicate records. The software was written internally to do this work. The next step was gap filling. This was done by using, it says duplicate records here. These are actually parallel records where we've changed the instrumentation, interpolation, and also satellite measurements. And then we formed composite records using the best available data sources. But this was just in stations where there were gaps, not all stations had gaps, obviously. So in Ireland, the sunshine duration has traditionally been measured using Campbell-Stokes recorder, but in more recent times, as the synoptic network has been automated, they've been replaced with KIP and Zonin CSD3 automatic instrumentation. The manual stations we have, the climate stations we have in the country, they're manual also, but they only do readings once a day. And there's a problem in them, and that we don't get readings at the weekend, so cards aren't changed, so it's a bit of a problem with them. At our synoptic stations where we do have the 2 instruments, we found that there's about a 15% difference in the sunshine durations from the automatic measurements compared with the manual measurements. So where there's stations where they've only got automatic stations now, we had to convert the records into either Campbell-Stokes or KIP and Zonin equivalents. We decided for this set of normals to use Campbell-Stokes, as most of the data is still in Campbell-Stokes measurements. And in order to do this, we looked at the literature and tried some of the methods in it, but the problem we found with it was that at times we got very high values which weren't realistic, and sometimes even negative values. So Conal came up with a different method himself, and in this method what he did was he took the absolute daily sunshine duration and divided it by the respective daytime lengths. Then he plotted the automatic versus the manual. He binned the data, so he has lines here you can see here. So for example, if the automatic value is in this range here, you get a mean Campbell Stokes equivalent reading here, and this is the value used. By changing the width of the bins, you can make it the more tight or less tight, depending on how much data. One thing was, unlike Frank, who has very good parallel measurements, at some of our stations, the parallel measurements were only for a very short time. So this calibration is done on all the parallel measurements for the whole country, rather than for each individual station. And after you do your correction, then you calculate back to absolute daily duration by multiplying by the daytime length. Okay, so the advantages of this over other methods that he looked at was that there was no assumption of whether it was linear, quadratic, etc., and it never produced impossibly high or negative values. And the same method proved suitable for converting satellite measurements as well as the Kipton's own measurements back to Campbell Stokes equivalents. Okay, so after the QC, the next step was homogenization. He initially considered 3 pieces of software. At the time when he tried to set up Homer, we couldn't get the packages for running or 2.15, which was needed to run Homer. So he couldn't get it running in the time frame. We've since got it from somebody else, so we have now got Homer running, so we may go back and look at it. MASH worked very well for the sunshine duration data, but for our diffuse radiation, we've very low data availability, and in some cases there were gaps in all stations, and MASH wasn't able to handle that. But Klimatal could run for the diffuse radiation. So as it could run for sunshine duration, global and diffuse radiation, it was used to homogenize the data. We found that there were one break in the global and diffuse radiation, both in the same station at different time periods, but we don't know the reason for this. With sunshine duration of the 21 stations, there were breaks in 7 stations, and they ranged from about 4 to 14%. So then for producing the climate normals, for the annual normals, you can see here, we have 5 stations with 12 months of global radiation. We've only 4 for diffuse. And then even though we had 21 stations for sunshine duration, we only actually have 12 stations which have a full year of sunshine duration. Similarly with days of sunshine, the same case, and we had even less than for daily sunshine duration. So to show you what these look like then on a map, it was decided that because, as you can see, we've only got 12 stations and they're all on the coast, so it wasn't possible in the time period before this talk to grid them. So at the moment we have the sunshine durations over the CM-SAF map. We hope in the future to try to combine the two and to actually grid the sunshine, because that's a project that people want. So from this, you can see that on the south and east of the country, were the highest sunshine durations, whereas in the west and the north, we had the lower sunshine durations. Looking here at Dublin, it's one region with 3 different locations with readings. This station here is close to the mountains, and it's a synoptic station, as is this station here, Dublin Airport. This station in the middle is actually very close to Dublin Airport, so we expected the 2 of them to be more similar. This one, because it's close to the mountains, we thought there could be a difference. But when we actually looked, this station here is a climate station, so it's a manual station with 1 reading a day. And at the time when it was homogenized, we didn't have a reason for the break, but since then we've discovered that there were glass houses built nearby, and that there's an issue with shading at a particular time of the day. When it was homogenized with Klimatal, the correction was applied to the early data set rather than to the end of the data set. So the decrease is because of this. So there was actually a 6% decrease we found in 1995, which wasn't bad because the greenhouses went in 1993, so it's relatively close, and it was a 6% decrease. But if we had actually applied the correction forward, it would be the same as Dublin Airport. So that's something we'll have to look at. We only found this out last week, because it's very hard to find metadata as well at times, but we solved the mystery last week and we'll fix it now in future maps. For the number of days of known sunshine, this station down here in the south had the longest duration of sunshine, but it also had the highest number of days with no sunshine. The East Coast, they were all very similar with, they had the most sunshine in the day. Then we looked at maximum daily sunshine duration. As you might expect, the station in the north of the country has the longest daytime in summer, so it had the highest daily sunshine duration, whereas the station down here in the south had the lowest. But there doesn't seem to be any kind of trend with latitude. So there may be local effects we don't know about. Once again, you can see here the effect with the exposure being affected at the station here. So you couldn't, it's lower than you'd expect. So it needs more work on it. Okay, so then we looked at a number of stations which had normals for the periods 1961 to 90, 71 to 2000, 1981 to 2010, and 1990 to 2020. None of these stations proved to be inhomogeneous either. And as you can see, this is for the total sunshine duration. The trends are very similar for all the stations. If you look at the mean here, we did get a dip in the 1971 to 2000 normals, and we think this is due to global dimming. And since that time, there's been an upward trend of about 3 to 4% compared to that period in the amount of total sunshine duration. Similarly, when you look at the number of years with no sunshine, this is also decreasing. And as you can see here, once again, you've got your 1971 to 2000 with the highest number of days of no sunshine. And the decrease is around 6 or 7%. When we look then at the yearly sunshine duration at Valencia Observatory, we have values from 1893 to present. You can see here that there was a decrease between down in the 70s to the 80s, and that's increased again. So we think that the next set of normals, that the trend between the 1991 to 2020 normals and the next set, it won't be as big a change because it should have largely leveled out because of this difference. So just to summarize the results of this, the solar climate normals have been produced. We have a little bit more work to do with the homogenization, just to fix where the station, for example, with Botanic Gardens, where the correction was applied to the early data, where really it should have been applied to the more recent data. The gridding, we're going to put more work into that before the end of the year, just to try and get a better handle on the whole country and not just use the satellite underneath. We found that the South Coast is the sunniest region overall, but it also had the most dull days. And we compare the new solar norms to previous sets, and we can see that it's increased, but we think that's due to recovery from global dimming. And that's everything. If anybody wishes to talk further, Connell Ruth, he doesn't have his email here, but I can put it in the chat if anybody wants to talk to him about any of the work he's did, or you can send me an email. So that's everything. Thank you.
Thank you very much, Mary. Are there any questions? Because there is some time left for questions. Can't see.
There's a question from Peter Domanko, Singe.
Oh, yes, please, Peter.
Good afternoon for everybody. Mary, you have mentioned three kinds of homogenization methods at the beginning of your speech. The Homer, MASH, and Klimator methods, and from these three you selected the Klimator. I ask you why you left out of consideration Acmant. Do you know Acmant method, or in spite of you know it, you have a bad opinion about this method, or what is the reason?
No, it was basically there's time constraints, and we have most experience with MASH. We think MASH is a very good method for using, but it just didn't handle the diffuse. So just with time constraints of getting the normals done this year, we just used those three methods to get it. And Homer, actually, the bits of Homer and MASH that for the sunshine duration, they actually agreed very well, the three methods. So we didn't look at any other methods, and that was the only reason for it. I know that Acmant is a very good method too.
Okay, thanks.
Okay, then one question from Gerard.
Hi, Mary, this is Gerard. I was wondering, in your efforts to grid the sunshine duration, did you consider to use the satellite information in this gridding as well? There's a paper which Christoph Frey has drawn my attention to, where he does this same trick for Switzerland, where he merges the station data with the satellite data in such a way that you can get a field which covers the whole country. Was this something which was which you tried, or you haven't done this yet?
No, it's actually our next step. Barry, who's mentioned on the paper, he has just started to look at this, and we're also going to have a look at reanalysis data as well, just to see how it compares as well with the three different ones and try and incorporate it. But thank you very much. I'll have a look at Christoph's paper. I didn't realize he had one on it, so that's great to know.
Great. Okay, thanks.
Barbara?
Yeah. Mary, when you look at the differences between the automatic measurements and the Campbell-Stokes, have they been the same for all the stations?
It's a bit of a problem in that you can see there's a bit of sorry, I don't know if I can go back on my just go back here. You can see here like the variation in them, but the one problem is that some of the stations we have very little overlap. You know, it went from manual to automatic very quickly. We're hoping at our airports, they still have both manual and automatic. So we're trying to get a longer parallel series there so we can have a more detailed look to see how they compare. But at the moment, we didn't have enough data to do the stations individually.
Okay, thank you.
Okay, thank you very much, Mary. The oral presentations are now followed by a poster presentation about new Slovak climatological normals for the period 1991 to 2020. And it is sorry, can't hear now. I'm here again. It's given by Ladislav Markovic from the Slovak Hydrometeorological Institute. Okay.
Do you hear me?
Yes.
Good afternoon. Good afternoon. I'm sorry for delay. I'm not sure if I'm sharing my screen. Can you see my screen?
Yes.
Oh, I'm glad. So I'd like to give you a short introduction to work that we are doing at Slovak Hydrometeorological Institute. And it is in a poster form. This poster deals with work that was already done in a calculation of the new Slovak climatological normals for the period 91-2020. As we all know, this is the time when all services prepare new climatological normals. in Slovakia, we also are trying to meet all criteria to prepare these normals in time. Currently, we are preparing with my colleagues, Oliver Bochniček and Peter Kajaba, normals for temperature and precipitation that will be presented in this poster. As we all know, climatological normals are very necessary for comparison of the current state of climate with long-term state of climate, and they represent the most likely condition in a given place. Therefore, they are necessary to calculate these normals, even if in current climate conditions, the climate is not stationary, and these normals may not always represent the real condition in this place. As we can see in our poster presentation, we focus on temperature and precipitation. Temperature data was used in calculation of new climatological normals, was used from 84 climatological stations. And we also met all WMO guidelines necessary for the calculation of climate normals. But in some stations that can be seen on this map, I hope you can see it, that are represented with blank squares. It was not possible to meet all necessary conditions given by WMO, but these stations were all nevertheless selected for calculations because they are in an important place and necessary data were filled. For precipitation stations, we use a wider network of precipitation stations. I believe it was more than 500 stations. And these stations were also separated by virtual stations that were used in preparing of mapping results. My colleague Oliver Bochniček focused on air temperature. It's very necessary to calculate also monthly mean of air temperature, maximum and minimum air temperature, but also derived characteristics are very important and can show us changes in the climate. Oliver decided to present you in this poster number of days with temperature. In this poster is temperature bigger than 5, 10, and 15 degrees Celsius. It was important to focus on these temperatures because in our country is seen not only changes in absolute number of days with temperature bigger than 5, 10, or 15 degrees Celsius, but as presented in this poster, I'm sorry that I'm shifting and resizing, but as you can see in this poster, there will be, I believe, attached in some papers from that you can access. It's not only changing number of days, but we can see onset sooner. These days are, for example, with temperature bigger than 5 degrees, this period is starting sooner in whole of the territory Slovakia, and in some cases it is more than 10 degrees sooner than it used to be. So the period with temperature, Celsius temperature is increasing. Interesting is when we focus on, for example, days with temperature bigger than 50 degrees Celsius. In mountainous areas, is onset of these days increasing more than 10 days in comparison with 1991, 2020, and 1981, 2010. So it's only 10 years later, we can see that almost more, in some station 12 days, this temperature, basically the temperature became 12 days earlier. So it's everything is shifting, is changing. it's also necessary to tell that in addition to significant acceleration of air temperature, it's visible also positive shift in all altitudes and in whole territory of Slovakia. These shifts influence not only planning in agriculture, transport, sports organizing, tourism events, but they are also important in consideration with other climate meteorological characteristics, as precipitation, that it is not falling as snow, and so on. In other part, I prepared some maps of new climatological normals presented for the year. For the warm half of the year is April to September, and so on. For example, summer, winter, number of days with snow cover, number of with precipitation bigger than 1 millimeter. These maps don't show the full picture. It's very important to say that in Slovakia, in comparison with the previous normals, mostly with 1990 normal, we can see shift not only in number of days with precipitation or days with snow cover. There is very fast decrease. You can see very fast decrease in number of days with snow in the lowland regions. But in summer months and winter months, we can see that pattern of precipitation is changing. And in summer months, convective precipitations are really changing the spatial and temporal distribution of precipitation within our territory. This is end of the data that were presented in our poster. But in the next part of our work at Slovakia Hydrometeorological Institute, we are focusing on all necessary characteristics. For example, number of days in temperature, number of days with temperature bigger than 25 degrees Celsius, tropical days, number of frost days, and so on, to create complete picture of new climate that is currently being observed at our territory. And these outputs are very necessary because currently used characteristics, currently used normals does not represent correctly climate that is observed in our territory. And it's very concerning to see what pictures, what temperature, what precipitation actually is new normal for the period 91-2020. Thank you.
Thank you very much. Are there any questions? Yes, I see one. Please.
It's me again. Thank you. Thank you very much for presenting your poster. One question: in the poster, you have homogenized the variables using the MASH.
Yes.
Which could you please also indicate the method that you use to produce the maps?
Yeah. You mean precipitation maps?
Yeah.
Yeah, precipitation maps were created by IDW, inverse dimension weighting. It was created in ArcMap, and it was created. My colleague created methods that use IDW and incorporate also, as you can see from the maps, altitude. It's in whole method, but it's mostly based on IDW.
Thank you very much. Yes, thank you.
There is another question from Dan.
Yes, thank you. Thank you for an interesting presentation. In your temperature maps, the third row of maps is to do with the onset of 5 degrees, 10 degrees, 15 degrees. Can you explain what you mean by onset? Is that first day or a period of days above temperature?
Yes, exactly. It's meant as a first day in which this temperature was recorded as in the calendar year. So we can say it was 5 days earlier than in previous normal.
Okay, so okay, that's great, because I think sometimes you can have a warm spell early in the year and get a sort of almost like a false start, I suppose, to the
but it's not meant as a period with continuous. Okay. It's meant as a first day. I didn't correctly.
Okay, thank you.
Thank you, Ladislav, for your presentation. And we have now time left for a discussion on the whole session. But first, I wanted to ask if there are questions for Andres Chatara from EUMETNET, because we didn't have time to formulate questions. Are there any? I don't think so. Are you here still, Andres?
Yeah, yes, I'm here.
You're here, but because you showed the changes of the Köppen-Geiger maps and so on.
Yeah.
Have you also found changes, remarkable changes in vegetation?
In precipitation? Well, I think most of the changes are caused by the temperature trends, because in the precipitation it's probably that we have noticed slightly a decrease of the precipitation, but not very significant. But as the temperature has raised, the changes, I think they are caused by the temperature mainly. Yeah.
Okay, but with vegetation, I meant, are there significant changes?
Yes, because in spite of the precipitation is almost the same than in previous decades, as the temperature have risen, there is more evaporation. So there is, we don't have so much water for the plants as we used to have.
Okay.
So yes, it's there are a lot of articles, a lot of press released about the certification in Spain, because it is expanded clearly in the, for example, in the southeast of Spain, that it is a very arid region. There are many signs of that the desert is growing. Yeah.
Okay, thank you very much.
Thank you for your question.
Now we can move the discussion on session 1. And from my opinion, it was the focus was also very stressed on the fact to communicate the correct climatic information to the public by different means. And it's also very necessary to communicate it very clearly, communicate, for example, what is the reference period, and if you compare it to anything else, then you should use the same reference period and so on. Are there any discussion on that? What is the statement of WMO, for example? Yes, please.
I don't want, of course, to make a statement, but rather a question, just in addition to what. If the people that are involved with this work for many years, do they feel that there is a need for common by all agencies, I mean, throughout Europe at least?
we can't hear you again.
The question is, do you feel that there is a need of a common reference period for the meteorological services, at least for Europe, for the...
Well, that's a question that I put in, well, I rise to consideration, because yes, it's very common to compare trends between different countries, and it's very confusing if they are not referred to the same period. So something that I put to discussion.
So if there's a guideline from the WMO towards this direction? Or...
No, if I'm not that I'm aware of, but I suggested the 30-year just as to be, well, the same time span which is recommended for the normals. So it would be kind of normal, although probably for communication to the media, we would update these trends of 30 years every year. But anyway, and yes, it's a problem. It's linked also to the presentation by Monica about the extreme precipitations and extreme value adjustments with the generalized extreme distribution. And on the one side, we need the longer period available to adjust reliably the distributions to extreme values. But on the other side, if we take a very long span of climate data, in the context of climate change, we will be mixing populations, statistical populations, which are different. So we must find a compromise between having a long period for adjustment, but not mixing not adjusting to the climate, to the current climate, not to the past climate, which can be different.
Yes, please, Joseph.
Well, I think that selecting the reference period as was defined, by the way, Jose saw the guide on the climate normals. And in this guide from 2017, I think, it is written that the WO is recommended that the period from 1961 until 1990 will be the period for long-term records assessments. So if we are dealing with climate change monitoring detection, we should use this standard normal reference period. But from time to time, I hear it when you need to say something for different sectors. I'm looking for more operational things. And when we are speaking on climate models and their projection, sometimes people say, don't speak with me about the temperature that was during the previous 60, 70s from the previous century. I would like to know how the temperature will change compared to the recent period, not to the previous 1961, 1990, because we know what the climate is. This is what we already undergoing, and this is what we know in the last 30 years, for instance. So please tell us what the climate projection, the forecast relative to the last period and not relative to 61 and 90. And regarding communicating the things, I think that Frank showed it very clear that this is really important to which reference period you are talking, because the public don't remember what was during 1961, 1990. And if in the news you are all the time says the temperature was above the average, which average? 1961, 1990? Remember it. And so every news will start with the temperature was above, the temperature was above, the temperature was above, because 1961, 1990, as we saw in all the presentation during this day, is a much cooler reference period. So for climate monitoring, I think that we should all stick to the WMO recommendation, but for public and communication, maybe for different sectors, by the way, we need maybe to think on different climate references. Thank you.
Frank?
Yeah, I just want to confirm what Joseph just said. I think it's exactly the argument that is given in the WMO documents. And for example, if we look at the farmers or the agricultural sector in Germany, we know that they adapted their crops to the meteorological conditions they have seen during the last decades. So for them, it's relevant information to compare the current status with what they are adapted to. And that's not the climate of 1961 anymore. So, but I tried to make this clear. So in DWD, we made that decision. If we talk about the communication of long-term climate change, then it should be a reference point that is further back in time. So where we did not have such a strong climate change as today. But for a number of applications, especially in agriculture, for example, we try to look what is a relevant time scale of those who make the decision in that sector. And that could be the last few decades. And I think that's exactly the argument that WMO is giving in their guideline. But it would be interested if others have a different approach. So there was also this questions about consistency of agencies in Europe, and we would be interested in that. We try to get into discussion with at least our German-speaking neighbors, Switzerland and Austria, and to see how they communicate it, because that is noted by the German press.
Okay. Other comments from Austria or from Switzerland here?
I can comment for Austria.
Yeah.
Can't
see you.
We had one.
Oh, it's okay.
We had for a long term the 1960, 1990 mean, but in the meantime, we already also apply other reference periods as is necessary for the different tasks. And on the climate monitoring portal, you can choose to which reference period you would like to see the differences.
So could it be that you have, for example, for agriculture, you take another reference period than for glaciology or whatever? Or should this be consistent? You know what I mean?
About, I think there should be as much consistency as possible in the things you provide. But if it doesn't make sense to take the same period as for any other application, you have to change it.
Okay. Are there some additional comments on that? For example, what is Hungary doing? Monica?
We use the same reference period for all the sectorial information.
Yeah.
Recently, we changed to the recent normal from 1991 to 2020, at least in our monthly and yearly reports. But if we would like to point out the climate change, we use 21. No, we use 61 to 90 to our analysis as a reference period.
Okay.
And we regularly communicate the linear trend and the change derived from the linear trend. I mean the slope multiple with the period of the change, but it's really hard to explain to the public that the change for the whole period, for example, from 1901, what we analyzed, is smaller substantially than in the very last period, from 1981 to nowadays. So it's not so easy to explain. Possibly the decadal change would be the proper characteristic to highlight the speed of the change.
Thank you, Monica.
And I also would like to reflect somehow what Josie mentioned for the precipitation series to analyze the extremes. Yes, Jose has right. The general extreme value distribution is valid for independent and identically distributed sample. That's right. But I agree that we have to somehow compromise between the length series and the fitting. But on the other hand, there is a method, or there are methods to make a distribution fit for non-stationary examples as well. So there are functions in R, for example, what you can use for samples where are non-stationary. So thank you.
Thank you, Monica. Any additional comments? If it is not the case, I would propose to close the session, but before that, I want to thank the speakers and the participants for their contributions. And we now have a break for half an hour. And thank you for listening.
Thank you very much for chairing this session. We will reconvene in 28 minutes. Thank you very much.
Thank you.
Thanks.
So if we aim to provide a data set with a long historical record, the only possibility is to use the sunshine duration records as well, because we think that the global radiation data only are insufficient. When looking at the two maps in the on the lower part of the diagram, it's clear that there are other problems as well. So when you look at the map for the global radiation measurements on the left, you see that this network is fairly homogeneous over Europe, and the color coding gives you the elevation of the station. Whereas when you look at the sunshine duration records, you see that there may be much more records, but they are very inhomogeneously distributed over Europe. So, well, the network of sunshine duration measurements has problems as well, as you see. Most of these data are provided by the European Met Services, who kindly responded to our query. But a lot of the data from the global radiation measurements also comes from the World Radiation Data Center in St. Petersburg. And we also managed to get some data from the Baseline Surface Radiation Network. This is a very low density network, but with extremely high quality stations. So they are a bit of the anchor points, so to say, of this data set. Now we come to the question how to convert the sunshine duration measurements to global radiation. And the standard approach to do this is a linear Angstrom-Prescott relation. However, when experimenting with this, we thought it would be more wise to use a more recent approximation proposed by Harry Cirque some time ago, and that is a nonlinear relation. And when you see the scatter plot in the lower left-hand corner, you see measurements for the build in the Netherlands. And on the vertical axis, you see what is called the daily clearness index. So the observed amount of global radiation divided by the global radiation at the top of the atmosphere. And on the horizontal axis, you see the daily sunshine factor. So the observed amount of daily sunshine divided by the maximum amount of possible daily sunshine which is available there. And what you see is that in this scatter plot, and when you plot a line through it, then this is not a straight line, but it is a line which curves downwards when you go to the lower values. And the interpretation of this curve is that when the cloudiness increases, clearly the amount of radiation and sunshine decreases as well, simply because of the coverage of the skies. But the clouds themselves become thicker as well. So there is an additional effect which filters away some of the radiation, and that explains this additional downward curving of this line. So the relation we're using is on the right-hand side of the slide, and the parameters are this K clear, which is about 1.7, the clearness index for a cloudless day. Beta and gamma are parameters of the model, where the gamma here gives the nonlinearity of the model, and S is this time fraction of bright sunshine. And when you move this relation to the situation where you have gamma equals 1, then you are back in the Angstrom-Prescott relation. So what we did with this relation is that we looked for stations which have overlapping data for both sunshine duration and global radiation. And we use this overlapping data set to provide an optimal parameter estimate of the 3 parameters in this relation, which I showed in the previous slide. And we did that for all available stations we have in Europe. And what you see here in this slide are the 3 parameters and their optimal value, in this case for summer, but we did this for every season. And it's clear from these maps that there is not one uniform value which is optimal for the whole of Europe. You also see in the middle graph that this gamma parameter is not equal to 1. So there's a distinctly nonlinear signal in this relation. And also that there is quite some difference between stations within Europe regarding this nonlinearity. And similarly for the beta parameter, which varies quite strongly across Europe. Interesting is that some stations in Spain are close to providing a linear relation between sunshine duration and global radiation, but that other stations have much smaller values of this gamma, therefore also being much more non-linear. Okay. Another issue we have to deal with is the quality control. Although we are working on more advanced quality control methods together with the colleagues from the Czech Republic, from the GCRI Institute, here we simply apply a quality control check based on physical limits. And we have a very rather crude way of doing this. And we simply use this rule, which is from the literature, where the maximum observed amount of global radiation at the surface relates to that of the global radiation received at the top of the atmosphere on a clear day, on top of the atmosphere, and there's a parameterization of the elevation of the station. So this is a very crude way, but it works quite well. And the source for this relation is that it's a linearized version of Beer's radiation extinction law. When you apply this quality control rule to some of the data, and I have two examples here, one from the station in the Netherlands called Kabau, and one from Tromsø in northern Norway. You see that the upper limit of this particular relation, which is this black line over here, seems to describe the maximum values of the global radiation quite well. The lower limit, which is barely visible in this plot, I'm afraid, is about the 3% limit of the top of the atmosphere radiation, and that is also a limit taken from the literature. To experiment, we also used a limit which is used in the community of the baseline service radiation network. So the people who are provide these high quality stations, and they have what is called a 1 minute extremely rare limit. And I've integrated this limit over a 24-hour period, and what you see is a maximum amount which is quite a bit higher than the amount we are using in this test. Perhaps not surprisingly, by the way. So for Tromsø, we see there are more data which violate this maximum amount, and we think this relates to the snowy conditions in Tromsø, where especially in spring and in autumn, we see violations of this maximum amount. Okay, so after converting the sunshine duration measurements to global radiation and performing some rather simple quality control on these in situ measurements, we would like to grid these data to provide a gridded data set over the whole of Europe. And the way we proceed is by using patterns of dominant modes of variability, so patterns based on satellite measurements. And the satellite we are using is an American satellite, I'm afraid. It's a Ceres satellite. This is a satellite which provides data for a larger region in Europe than the European products. And we use the spatial covariance from these satellite observations in this gridding process. And this approach has been inspired by what is called the reduced space optimal interpolation technique, where you fit dominant patterns of variability to your in situ data. The dominant modes of variability are calculated here using self-organizing maps, which is a method from machine learning techniques, or And what you see in this picture are the first 15 of these maps we are using in this procedure. We are a bit, we are hoping that by using these patterns, that the fit to these patterns cancels some of the noise we introduce with the conversion from sunshine duration to global radiation. So this scatter plot I've shown in a previous slide clearly gives you that there is a bit of scatter there, and hopefully with this approach we can filter out some of that scatter. There are also other points which need to be mentioned. There is not a clear ordering in the patterns we are using to fit the data to, and also the patterns don't have much of a structure, and that is a bit of a disappointment. So we were hoping to have more detailed information on, for instance, topography or land sea contrast or whatever when it comes to using these patterns. So there is so we still need to do some research on that to get this more clear. However, when we take this approach and we calculate a gridded map and we compare this gridded map against the original observation, so simply to check how well we are doing in reproducing the observations, what we get is a picture like this, and this is for the summer of 2018, where each dot represents a station. And the color coding gives you the bias between the actual in situ observation and the gridded EOPS value for the corresponding grid box statics. And what you see in that areas which are data rich, like the central part of the map, so Germany and the Netherlands and France and areas around that, the bias is rather small. But when you move a little bit more to the west or to the north or to the east, or you move to stations which are at a higher elevation, like in the Alps or in the Pyrenees, you see that the bias increases a bit. Similarly, when you look at the standard deviation of this difference between the in situ measurement and the gridded data set, you see that the standard deviation is low in this data-rich area, but it gets higher when you move to more the outside of the domain. Also, when we compare our gridded method to the satellite measurements, in this case we use the Meteosat second generation data to do that, and this is a picture for August 2018. What we see is that in the central part of the domain, so again in this data-rich area over Germany and France and the Netherlands, the bias is not very large. But when we move more to the east, to the northwest or south, where the station density is a bit lower, we see that the bias rapidly increases. And especially this is the case in the eastern part of Europe, where the bias is exceptionally large. Similarly, the standard deviation of this difference is small in the data-rich areas, also here very small over Spain, but again, moving south or southeast, we see that the bias of the standard deviation of this difference series increases very rapidly. So despite this not so good news, perhaps, we did do a test in how well the data sets we have can be used for research purposes when it comes to, say, looking at trends, for instance. And by using the package Climatol with some help of Jose, we homogenized some of the station data, and what we show here is the difference between the station data and the gridded maps. And this different series is then tested for any breaks using the standard normal homogeneity test. So I'd like to stress that the data set itself is not homogenized. We are comparing now the data set against homogenized data. And what you see is that in the light blue stations, we could not find a test, so we think these areas are homogeneous. But in the darker dots, we have found at least one break. So there are quite some regions in this data set where you have to be a little bit careful when you want to apply a trend analysis here. And for the white stations, mostly here in the northern part of Germany and the Netherlands, the data was of insufficient length to produce a conclusion. So we have tried to produce a dataset with gridded values based on in situ global radiation measurements. This is a mix of actual global radiation measurements and measurements converted from sunshine duration measurements using a nonlinear transformation technique. We found that there was a distinct nonlinear character in this transformation, so that is an interesting observation in my view. We used a rather simple quality control using physical and reasonable limits, and using a gridding method inspired by the reduced space optimal interpolation technique. We see that especially in areas which are very data rich, this technique smoothes out some of the noise, and the bias in these data rich areas seems rather small. However, in the areas where the station density is not very dense, we see larger biases. And what we think we need to do is follow this suggestion by Christoph Frey, which we mentioned earlier in the discussion related to Mary's presentation earlier today. Christoph used a combination of the satellite patterns plus kriging, and I think we really need to do the same here for this European dataset. So this is not the end, and this is simply a work in progress. So when you use the data now, you have to be careful. So it may not be too bad in data-rich areas, but outside there, it's you have to be careful. For trend analysis, you can use it, but be careful, it's not homogeneous everywhere. And there seem to be some issues with the most recent part of the data set, which we haven't solved yet. So I'm afraid this is not all good news, but it does conclude my presentation. Thank you very much.
Thank you, Gerard. So at this time, we don't have so many time for questions, but I think we can leave this for the discussion part at the end of the session to compare the results of different data sets. Okay? Thank you, Gerard. So we pass to the next speaker, Semho. I cannot pronounce this name from
John Simonke.
What is the name? Sorry.
Semyon Szymanka.
Szymanka. Okay, welcome. And you can speak here about Copernicus European Regional Reanalysis. Go ahead. And thank you very much.
Yeah, good afternoon. So I hope sharing my screen is working and you hear me.
Thank you.
Great. Yeah, my name is Semyon Szymanka and I'm employed by SMHI in Sweden. And I'm happy to show you some results and basically the service that we're providing to Copernicus about the regional reanalysis for Europe, a service that we are providing together with our partners from Meteor France and Met Norway, by the way. So that's yeah, I even managed to change the slides. Great. The service is running now for almost 4 years, or a bit more than 4 years by now. And you can actually basically split the service into 2 phases. So at the very beginning, or the first 2 years, we inherited model systems from the EUERA FP7 project, where they were set up a couple of regional reanalysis systems. And we use then inside the Copernicus service, we use the EUERA Harmony system and the Mescan Surfix system to produce then regional reanalysis operationally. So monthly updates of these data sets. And part of the work was then also to publish these data sets in the Copernicus Climate Data Store. In the meantime, we developed actually new systems, and these successors of these systems are there are now 3 components. So there's the Sarah Land system, which is the successor of the Mescan Surfix system. Then there's the Sarah dataset. So now it stands for Copernicus European Regional Reanalysis. And then the new components is actually an ensemble system. So we're running also the Sarah system with 10 members at a somewhat lower resolution. And the status in the moment is actually that Sarah and Sarah EDA production concluded recently, and we're working on publishing this data in the Copernicus Climate Data Store, but they won't be available before beginning of next year. Sarah Land, the production is still ongoing, but production might finish early in December. That's our best estimation in the moment. Yeah, perhaps very quickly, I was not completely sure about the background, but I think I show one slide about what actually reanalysis is. So reanalysis is actually the best combination of 2 worlds. So we have the observations and we have a numerical weather prediction model. And we use the observations to correct the model at certain times. So in the EUERA setup, that was actually every 6th hour, and in Sarah's system, it's every 3rd hour. So we keep the model system as close as possible to the observed values. And by doing this over a long period with the same numerical weather prediction model, you have this frozen system, then you create long time series with homogeneous quality and no gaps in time or in space. So these are the big advantages of reanalysis data sets. And of course, also complete parameter data sets. So some parameters which are not observed at all places, you still get a coverage in the entire domain. A little bit quickly about the data. So we're talking about the European reanalysis. So on the figure, you see the domain which is covered by this data set. So entire Europe is covered, also the entire Mediterranean Sea, for example. And there are plenty of parameters. So at the surface, we provide in the moment 36 surface parameters, but there are also parameters on throughout the atmosphere. So we have parameters on pressure levels, on height levels, also quite restricted, but there are also some data on model levels. And if you're interested in soil parameters, there's something in the SARA system itself. But if you're interested in that, then you should also go for the SARA land system, actually. Quickly also a little bit about the system, how we produce this. I mentioned that there are three components. So there's the ensemble system, SARA EDA, which has 10 members. So this is actually driven at the lateral boundaries conditioned by the ERA 5 EDA system. Then we use information from background fields, or we use information from SARA EDA and putting this information into the background fields of the high resolution system SARA, and here we use ERA 5 as lateral boundary conditions. And then in the last step, we are using SARA data actually as background fields into the SARA land system. For those who are more familiar with numerical weather prediction models that are around, quickly, so this is based on the Harmony scripting system using the Aladdin physics package. We are using 3D VAR for the upper air observations and optimal interpolation for surface observations. Yeah, and then there are a couple of improvements compared to the former ERA Harmony system, as for example, that we're now assimilating also satellite radiances from a couple of satellite systems. Perhaps SARA EDA very quickly, I mentioned 10 members, somewhat lower resolution, same resolution actually as the ERA Harmony system before. And then SARA Land, our land surface model, where we basically have analysis of daily precipitation, and then in addition, the land surface model based on Surfix 8.1. Or you might ask actually a question if there are global reanalysis available. So why should you produce something which covers only a smaller region? And quick answers, of course, you can add more information if you go to smaller scales, and that's the entire idea, which is also shown here on this slide. In ERA 5, we have rather coarse resolution, as we can see here in the land sea mask. The resolution is much higher in the SARA dataset with 5.5 kilometer resolution. The coastline is much better represented, or also lakes or islands. So what we see here is actually Denmark and southern Norway and Sweden and the very north of Germany, for example, and islands as the island of Bornholm in the Baltic Sea. They are hardly represented at all in ERA 5, whereas they're quite good visible or quite good represented in the SARA dataset. Another example would be actually adding information to the system in terms of topography. Now we're looking at Central Europe and the Alpine region. So we clearly see that the Alps are much better or more realistic represented in the SARA dataset compared to ERA 5. And I mean, with adding these information at the surface, as surface roughness and so on, so the system is able to represent some of the features as temperature or precipitation better as in a rather coarse model setup. And now we're looking a little bit into the data. I will start with an example of an extreme event which happened in January 2005, actually in southern Sweden. So the storm Gudrun. Actually 7 people died during this event, and was really one of the most severe storm events ever registered in southern Sweden, with really large devastation in terms of lumber and forest that was destroyed. So really one of the major storms, and we had a look how the data sets, how ERA 5 and SARA actually compared to observations and to each other. So we see here the top figure is ERA 5 at the culmination of the storm, and the bottom panel figure is SARA data. And on the first view, you see that there are in general higher wind speeds in the SARA data set compared to ERA 5. And then if we look at some features, as for example, over the bigger lakes in southern Sweden, you see that they stick out somehow with higher wind speeds. or in the opposite is actually the island of Bornholm, which I mentioned earlier. You clearly can see a reduction of the wind speed over the island, which is then related to larger surface roughness over the island, and that's not represented in the ERA 5 dataset. So the first impression is already that the storm is better and more realistic represented in the SARA dataset compared to ERA 5. And if we compare now to observations, it's two locations. So A here at the southern tip of Sweden, we have in red the observations, and in green the SARA data, and in blue is then ERA 5. And similar to the first, or according to the first impression that we have, that the wind speeds are higher in SARA than in ERA 5, we see now that this is also actually more comparable to the observations that we have from this storm. Similar for the second station, also here again in blue, the ERA 5 observations, which do not reach these high wind speeds as they have been observed, and as they are also represented in the SARA dataset. So that was more a single event and an extreme event that we looked upon first. So now we're going a little bit more into statistics. So these are over longer period differences in wind speed between ERA 5 and ERA in this case. It looks the same actually for SARA. So what we see in general, the differences are rather homogeneous over the open ocean. But when we come into regions with strong topography or gradients, or as the coastline, we see actually that these data sets differ quite a lot on smaller scales. So that is what we investigated then in more details with some statistics. So we picked actually stations in Sweden only which are along the Swedish coastline, representing these areas where the data sets really differ a lot, and did a comparison to observations. So now we have these 4 data sets: observations, ERA 5, so the global data set, ERA Harmony, and the SARA data set. And we take data from 30 stations along the coastline, hourly data for the period 1996 to 2018. So quite a long period, and hourly data that this is a long or data series with a lot of data points. And focusing perhaps here on the root mean square error and correlation, we see clearly that the SARA data set has the lowest root mean square error and highest correlation, so outperforming actually both data sets, the ERA Harmony data sets and ERA 5. Similar exercise now for 2-meter temperature, but the message stays the same. So also here, SARA is outperforming ERA and ERA 5 also for 2-meter temperature. Some difference that I should mention here is actually 10-meter wind speed is a parameter which is not assimilated into the system. So these observations are independent, or the reanalysis data is independent from the observations, but that's actually not the case for the 2-meter temperature. 2-meter temperature is a parameter which is assimilated into the system. Yeah, but we see still the message is the same for both parameters. So SARA managed actually to assimilate the information better into the system than the data sets with a coarser resolution. Good question is also how homogeneous is the data set actually in time. So we have here 2 plots, one for ERA Harmony and one for SARA, showing actually the forecast skill over the entire period. So remember that the ERA Harmony series starts in 61, but SARA only in 84. So the SARA plot is representing a shorter period. And we concentrate a little bit on the red line, which is actually the standard deviation between the 30-hour forecast and the 6-hour forecast, which are valid at the same time. But we think about it only as quality. So lower values indicate actually higher quality of the data set. And what we can see here is a jump in 79, and that was for the ERA Harmony data set, and that was actually the switch from ERA 40 as the lateral boundary condition to error interim. So with that jump, or with this change of the lateral boundary conditions, we got an increase of the quality of the error harmony data set. And then there's something else. There's also a slight decreasing trend over time in the standard deviation, which is also an indication for an increase of quality over time. And that's coming from the increasing number of observations which are assimilated into the system. So there's simply more observations are becoming available later in time. So there are more observations from airplanes, for example, in 2015 than there are in 1985. Yeah, the same trend we see actually for Sarah, but there's no kind of break since we're using error 5 throughout the entire series. Next slide, lessons learned actually between error harmony and the Sarah dataset. That's also about weaknesses that we discovered in error harmony, showing two examples here. So we had some issues actually after each assimilation of observations. The model was not really in a stable state. So we had kind of spin-up issues in the first forecast hours. So what we see here is actually 10-meter wind speed. Again, the same storm that I showed you earlier. And the red curve is actually coming is the 10-meter wind speed from the UERA forecast model. And what we see is actually every 6th hour, we have such a jump in the wind speed, which is due to instability in the system, coming from bad initialization of the turbulent kinetic energy. But if you see now the blue curve here, these are the results coming from the Sarah system. So this problem was actually identified, and then it could be solved for the next version. So these are definitely good news that these spin-up issues for the wind speed and also other parameters as maximum and minimum 2-meter temperature were affected, that this issue was solved. Second figure with the same message, this was for precipitation, also similar issues. So here in the first forecast hours, there was an underestimation of precipitation, which you see here is present in the first 3 to 4 forecast hours. Also here, that issue was solved in the Sarah system. So all what is left is actually this peak here around 12 and 15 UTC. But since this is representing a summer month, so this is the afternoon maximum of precipitation, so convective precipitation, since this is a summer month. So that's realistic, and that's good that it's there. But this underestimation in the beginning was really a problem of the system. Last slide. Snow depth. So that's coming from the Sarah land system. It's very preliminary. And what we see again in comparison, green is error 5, and red is Sarah land system, and blue is UERA, and black are the observations or saffron data, which we consider very close to observations. And we see actually here for the different altitudes that error 5 is seems to overestimate the snow depth at all heights or altitudes, and Sarah land and also the miscount surface data is much closer to the observations. Okay, and that's the summary, but perhaps I do not have to read it. Perhaps I have opened the floor for 1 or 2 questions if there's time. Thank you for listening.
Thank you very much for your presentation. I think this is very interesting for all of us, but I think we can discuss at the end of the session, like the general presentation, if you want.
Yep. Okay. Thank you.
Thank you. Well, we pass to the next speaker, Olivier from Hungary. The presentation is entitled Long-Term Grid Temperature and Precipitation Data Series in Hungary. Go ahead, Oliver.
Okay, I am here.
Okay.
I'll share the screen. You see the presentation?
Yes, I can see.
Okay. So my name is Oliver Szentes, and I work at the Hungarian Meteorological Service on the climate department. In our presentation, we present the production of a homogenized databases, which we use at the Hungarian Meteorological Service for climate studies. Furthermore, I show the temperature and the precipitation conditions of Hungary from 1870 to the present. We would like to create special and temporary representative databases. We have longer and shorter station data series. This unequal length is already a problem. Other problems with the stations is the coverage of stations unequal, like this map you can see. This row series include the missing data and also errors, and not least inhomogeneities, example due to relocation of instrument or methodological changing. Therefore, the available raw data sets need to be homogenized, quality control, and fill the missing data to produce good quality climate monitoring products. At the climate department of the Hungarian Meteorological Service, we use the mesh and MISH software to creation of representative climatological database. For temporary representative, we use mesh, and the MISH for the special representativity. The mesh is a relative homogeneity test procedure. It is a step-by-step iteration procedure. The role of series, candidate, and reference change step by step in the course of the procedure. An additive or multiplicative model can be used depending on the distribution of the meteorological elements. It includes quality control and missing data compression of model series. It provides the homogeneity of the seasonal and the annual series as well. Metadata probable dates of breakpoints can be used automatically, and verification files generated automatically. The homogenization of daily series based on the detected monthly inhomogenities. It includes quality control and the compression of missing data in daily data. The MISH, our interpolation software is MISH. The MISH consists in two parts. Modeling subsystem for climate statistical, local and stochastic parameters, and an interpolation subsystem. The modeling based on long homogeneous data series and supplementary deterministic model variables like height, topography, distance from the sphere. An additive or multiplicative model can be used, similar at mesh. The modeling procedure must be executed only once before the interpolation applications. The modeling is done on a dense grid. We use an half-minute resolution grid. The interpolation subsystem can be used the modeling parameters at the interpolation of the meteorological elements to any point of a grid. Here can use also background information, for example, satellite, weather, forecast data. This subsystem includes data series completion. It is a missing value interpolation for daily or monthly station data. Okay, let's look the homogenization of mean temperature. We use the 4 station system with different time over the total period, and the temperature additive model with significance level 0.05. On the right side, you can see the location of the stations with the temperature. The mesh fund system includes 19 stations from 1870. The mesh 2 system includes 33 stations from 1901. The mesh 3 system includes 55 stations, and the mesh 4 112 from 1975. The station systems at the temperature we knew in the last year, former from 1901, former we used 55, no, 25 stations from 1901 and 58 stations from 1971. Here is the most important verification statistics at newer mean temperature. The first for the critical values. The second row, you can see the test statistics before homogenization. These values are very large. The station systems series was very homogeneous. After homogenization, the test statistics in average was much better, around the critical value or below this value. The relative modification of series are in the fourth row, and the representative in the last row. In all the station system is the representative very good at temperature. An example for inhomogeneities for Pécs is a city, Pécs located in south part of Hungary. The row, you can see the annual mean temperature. The red line is the row series, and the blue the homogenized. The current location of the station is outside of the city at the airport. In the 19th century was the station on the rear side. Later, in the first half of the 20th century, the station was in downtown location. The 14 years, you can see other inhomogeneity from observation time changing. After the World War II, they relocated the station to the old airport, and the middle of the 15th years to the new airport. And here are other inhomogeneities due to instrument shear leakage. At precipitation, I used also for station systems, but at precipitation we use multiplicative model with significance level 0.01. Precipitation is a more variable element than temperature, so more stations are needed. The mesh one system includes 45 stations from 1870. The second system includes 90 stations from 1881. The mesh 3 system we use 131 stations from 1901, and the last mesh 4 systems we use 461 stations from 1951. And here is the location of the stations. And the most important verification statistics of the annual precipitation. After homogenization, the average statistics was very good. No systems below the Richter value. Due to great spatial variability, the representativity will be better at denser station systems. An example for inhomogeneity is precipitation, again for page. On the in the 19th century, the measurement was on the hill side. It was a better location than the current location on the hill. The end of the century in 1897 relocated the station to the downtown, and in 1907 was an instrument replacement. The old ring gauge used about 10% more precipitation than later instruments. After the World War II, there is another break due to relocation. After homogenization, we interpolate the homogeneous controlled computed series niche to a gradient dissolution of 0.1, which means there are 33 points in the case of Hungary, like this. Finally, the four gridded data sets are merged in a common database by taking the breakpoint values from the data set, which consists of most stations in the given time. In this year, we renewed the climate statistical parameters modeling for temperature. The using of formal modeling in the case of temperature was 57 stations data series. In this year, we renewed this with 112 station data series. Here you can see the average difference in spatial mix of mean temperature for the current climate period, normal period, compared to interpolation from 112 stations in different station systems. That was with the new modeling. The differences were similar at annual averages when we use 33 or 55 stations, but at month maps. After the new modeling, the interpolation was better. The spatial mean will be near same from fewer stations using former using fewer stations, the spatial mean average all months was higher. After the new modeling, close zero in all months. This average difference. You see the special means of temperatures in Hungary. The warmest years are in the last decade. It's not surprising. Before 1990, was only 3 years above 11 temperature, 1951, 1933, and 1872. Here are the environment temperatures in different climate normals. Only the last 3 climate normals are above 10 degrees. The lowest or 30 years normals was the first 30 years in the 19th century, end of 19th century, and the warmest the last 30 years. The coldest year was over the total period 1940, the warmest 2 years ago, 290. This year was the first above 12 degrees. You can see the linear trend estimation with confidence interval in all months and seasons as warming trends. Only the trends of October is not significant. Weaker warming is from 1870 in October, July, and September, and winter warming in the winter season from November to March, April, above 1.5 degrees. In January and February, the linear trend was above 2 degrees. The special means of precipitation, the precipitation is more variable in time than in temperature. The annual special mean is around, in general, around 600 millimeters. The driest is around or below 500 millimeters, and the wettest years was above 700 millimeters. The driest climate normals was on the end of the 20th century, and the wettest in the first half of the 20th century. The driest year was, the wettest year was 210, and the driest the next year, 2011. In 2010, the annual precipitation was in the mountains above 1200 millimeters, and the driest years, the most part of Hungary, was the annual precipitation below 500 or 450 millimeters. We use the exponential and estimation.
Sorry, Oliver, your time is ending, so please
I'm
try to finish.
Okay. The most months and seasons has negative trends, but these trends are generally not significant. Significant trends are only in April and October, and season spring. The precipitation increase is great in January, February, and winter, but not that significantly. From this year, free available daily gridded data sets in Open Data Portal from 1971 temperature, precipitation, station level, pressure, mean of relative humidity from 2001, global radiations, and index maximum or average wind speed. Summary: we created a representative parameter database with mesh with software, temporary representative series with mesh, and the special representativity gridded series with mesh. Better interpolation of temperature with the new model climate statistical parameters. The long-term changes, mean temperature is warming in every month of season, in general significant. The change of precipitation is mixed. And the gridded data series are available from this year on the Open Data Portal. Thank you.
Thanks a lot, Oliver. I'm sorry for the break I made.
No problem.
Thank you very much. So now it's time to have a little break.
If I may,
Mm-hmm.
sorry to intervene, but Semjon Szymanski has another commitment after the break. So please, if there are questions on his talk, can we take them now?
Okay, go ahead with the question.
Okay.
Question for Semjon, since he will not be here. You'll be joining after the break?
No, sorry, I can't join after the break. So if there are any questions, I would be happy to take them now.
But no, yeah, I have one question. When will this become available through the Copernicus?
So both the UR Harmony dataset and Miscan Surfix, they are available in the CDS, and the Sarah datasets, hopefully they will become available early in 2022. So the production itself, the production is ready, but the quality assurance is still ongoing, and we have to check that the data has no bigger breaks or obviously wrong trends that needs to be double checked now, and then the data will be published in the CDS. I can, yeah. Perhaps I can also mention that the negotiations with Copernicus have started last week actually for continuation of the service. So hopefully from early next year onwards, there will be monthly updates for the dataset. So the Sarah dataset is not supposed to stop in June 2021, but there should be monthly updates with a delay approximately 2 or 3 months after real time. There should be, the dataset will be updated in the next years.
Great, thank you very much. There are other questions for you?
Mm-hmm. Any other question for Gerard, for example?
Currently, there are not.
No.
I am here.
Yeah. Okay, thank you very much. We will resume in about 25 minutes. Yeah.
Okay.
Very much.
Thank you.
Thanks.
I think that we can start the last part of the workshop of today. So the floor is yours.
Okay, thank you. We have a poster presentation from Gerard for the KNME. It's a poster titled Developments in ECAT and the EOPS dataset. Gerard, are you here?
Yes.
Okay. Hi. Go ahead.
can you confirm that you see my screen?
Yes, I can.
Yeah.
Okay. So this is a poster giving a brief introduction into some of the activities we are doing with the ECA&D dataset and the EOPS data. And there are three things I would like to highlight, if possible, on this poster. So I've kept that very brief. One is that we are always looking for new data, clearly. But using the Aero4CS indices project, where Yolanda and other colleagues are associated with as well, which was led by Enrique Aguilar from the Tarragona University, we looked into a reconstruction of the climate in Europe in 1920 and 1921. And the reason for that is that 1921 is looking for the whole of Europe, still the driest year on record. And this drought in 1921 also triggered the huge famine in eastern parts of Europe, which was very strong in the Volga region, for instance. So we requested data from the Met services in Europe for this particular period and got quite a bit of requests. And we tried to make a reconstruction of the climate for that particular period. And as Stanos was so kind to give me 10 minutes, I added one slide from the publication, which has come out just before the weekend on this. In this publication, and with the colleagues of the Met services, we not only looked at the physical reconstruction of the climate, so what was precipitation and temperature, but we also looked into the impact of drought. And we think this is a bit of the way we would like to go forward when we describe huge climatic events like this. And what we did is, with colleagues, we looked into newspapers of 1921, where impacts of this drought were being monitored. And we simply collected all these newspaper clippings from 5 papers in Europe. So one from Great Britain, one from the Netherlands, one from Belgium, one from Germany, and one from the Czech Republic. And we categorized these clippings according to their particular kind of impact, like on agriculture and livestock farming, or on forestry, or on waterborne transportation and things like that. And based on that, we were able to give an indication when the first impacts occurred, which type of impacts these were, and when what was the period where the largest amount of impacts were actually being reported on. So that was an interesting thing. But on top of that, we also did the physical reconstruction, like what you see here are maps of the SPI for, this is autumn 1920, and this is the spring of 1921 and the summer of 1921, and the green and yellowish colors give drier than usual conditions. And the reason why this drought stood out is that not only that the summer of 1921 was very dry, but also the preceding seasons were very dry. So there was hardly any buffer left in the water reservoirs before the summer began. Okay. Another thing which we focused on in the last year or so is making a EOPS dataset for relative humidity. So again, using in situ data provided by the National Met Services, we provided a gridded dataset for relative humidity from 1950 onward. And what you see in this map over here is the data availability, and the light blue colors indicate that data availability is very high. So we've got 100% of, or nearly 100% of the completeness from 1950 until 2020. But in areas like Iceland, small parts of Norway and Finland, this data coverage is a bit poorer. And when you go to the east of the domain, the data coverage is quite a bit less. What we did for this data set is that we gridded humidity using this transformation, which works quite well for the high values of humidity. For the low values of humidity, we have a bit of a bias. This is shown in this particular graph, where on the horizontal axis you see the observed humidity of the station, and on the vertical axis you see the modeled humidity for a particular period in this in the modeled domain. And you see that for the high values, the two are more or less okay, they overlap quite well. But for the lower values, we see that the modeled humidity is a bit higher than the observations. Another new aspect of the EOPS is that we are trying to produce one for wind speed. Wind speed is notoriously difficult, as you know. Using optimal combination of covariates like topography, distance to coast, surface roughness, and a background field. We tried to make a data set for the whole of Europe. These covariates like surface roughness are the same data sets which Simeon uses for his regional reanalysis, and which we used, which you heard of earlier today. As you can see in this picture, which gives you one example for one particular day, we are not doing very well at the moment. So the coverage is not great, so we still need quite a lot of data to produce a Europe-filling data set. And it's also quite patchy, so especially over, for instance, Spain, we have a very patchy data set, so also there we need to step up our efforts. But another aspect which relates to this is that we would like to provide the EOPS also with an estimate of the uncertainty. And there have been publications where which show that the uncertainty provided with the EOPS is overconfident, so it's too narrow. So along with this new data set, we would like to introduce a new estimate of producing this uncertainty, and which actually expands the ensemble, the range of the ensemble quite a bit. And what you see in the lower two maps is the uncertainty estimate using the traditional method, which is on the blue colors, very low. But with this improved method, you see that the uncertainty estimate is quite a bit larger, especially in the areas where the station density is a bit low. So these are the most important aspects I would like to highlight in this poster. Thank you very much.
Thanks, Gerard. Thank you very much. You are very great, taking the correct time. Okay, thank you. So right now we pass to the discussion of the works presented in this session. So anybody wants to make a comment, a question about the three first presentations? Anybody? I want to make a question to Gerard. In your first work, you presented a database of rotation in Europe. This is available for use right now, or we need to wait some time?
Yes, it is already available, and you can access this dataset through the Copernicus Climate Data Store. But as I tried to point out, if you use it, you have to use it with care.
Yeah.
So unlike the wonderful reanalysis Simeon showed, which is a model product, these EOPS products are based on in situ data only, and they are by their nature a bit more difficult, in my opinion, to get right.
Okay, thank you, Gerard. Anybody else? Dan? Dan, go ahead. Dan Hollis.
Okay. Yeah, thank you. I was just seeing if I could start my video, but it doesn't seem to work at the moment. Oh yes, maybe it is working. So this is a question really, perhaps bringing together some of the aspects of the first session with this session. So in the first session, several people talked about the new 1991 to 2020 norms that everybody is creating. And this session is about data sets. So we had an inquiry a few weeks ago from somebody external to the Met Office who was interested in obtaining climate normals. I think it was across Europe, possibly even maybe across the world. They wanted a large number of sites for a particular project they were working on. And I struggled to find a single source of climate normals that somebody outside of the Met Institutes could go to and access that data. So I was just wondering what plans there were. So we will all share our data.
I'm sorry, but I can't hear Dan Hollis.
Through WMO, but whether there is a sort of data set of
Dan, excuse me.
NMSs across Europe.
Yeah. Can you hear me? Excuse me, but the sound and video frozen for some seconds. So could you please repeat your statement? Or
okay. Yeah, I was just trying to say that the different NMHSs in Europe will be creating the new 1991 to 2020 normals. And my question really is whether there would be any benefit in trying to bring together the results of all of those analyses into one data set that could be shared in one location. Perhaps the CDS, I guess, might be an obvious place for that. But that was based on my previous experience of struggling to find a single source of climate normals other than having to go to the websites of individual organizations. Does that make sense?
Hello. There is a place run by NCI, which is storing all climate normals which are communicated to WMO. I don't have now, and I'm trying to find the address.
Okay.
But I will send you or put in the chat tomorrow or whenever I have it.
Okay, that would be
It's a bit
useful.
difficult to discover, yeah.
Yes, I think for somebody, perhaps a non-specialist, shall we say, who might not be familiar with such data sources, then I think these things are quite difficult to find. And I think I did discover something, maybe it was the, I don't know, NCDC or something like that, and that had some 61 to 90 normals, but even then it was a limited set of stations and quite difficult for a non-specialist to get that data and make use of it, I think. So, you know, we all invest a lot of time and work analyzing our data, and I would imagine that climate normals in particular should be more readily accessible to users of that data.
Yeah.
Okay, thanks.
Thanks, Dan. Anybody else wants to make a comment or a question? About this session? Nobody else?
He's tired. It was a long day.
Yeah, I think it's at the end of the day. What? But
Currently, there are no other comments. Yolanda, I would like to thank you very much for sharing this session.
nothing at all. Thank you for the speakers and people sharing experience in this interesting workshop. Thank you very much for all of you.
Congratulations to all speakers of today. Please remember to send me your presentations if you haven't done it yet. So we'll meet tomorrow at 11 o'clock Athens time or 10 o'clock Central European time.
Okay.
Very much. Have a nice evening. Goodbye.
Goodbye.
Thank you. Bye.
Bye-bye. Thank you very much.
Thank you. Thank you. Bye-bye.
Okay, bye everybody.
Bye-bye.
Bye-bye.